welcome to Uhandisi Talks. My name is Marion Golder, and today I'm here with Engineer Rufaro from South Africa, a chemical engineer. She's joined us today to share with us her journey and some of the career option that you can have if you want to do chemical engineering, and some of the challenges she faced and how she overcame them, and some of the places where someone can work if they want to be a chemical engineer. So you're welcome, Engineer Rufaro.
Thank you so much, Marianne. Thank you for having me.
Yeah. Let's start with a short introduction, who you are, what you do, and then we'll get to your background.
Okay, sure. I'm Rufaro Mukwenya. I'm based in Cape Town, South Africa, but I'm actually from Zimbabwe, Harare, the capital. I have just recently graduated from my master's in the chemical engineering field that Marion talked about. And at the moment, I am working in research in the department that I completed my master's in, which is in biotech. So we currently specialize in using bioorganisms, microorganisms, to produce valuable products from otherwise non-valuable materials. But yes, I think that's as much as I can go to without giving up a lot of what we have in store for today's talk. But yeah, just a small little intro, yeah.
I have to say, I really didn't get much of anything with the biotech and all that. So you're gonna tell us more about that later.
Oh no, definitely. I will.
Yeah. So we're gonna get about that into that, and I'm sure the chemical engineers who will be watching this, they will understand better. Background, like chemical engineering, like when did this start? Did you was it like a dream you had, or when did this start? When did this journey start?
Sure. So it wasn't necessarily a dream that I had. All of my secondary school, I thought I was going to be a doctor. I thought I was going to do medicine. I thought I was going to be a doctor until I actually visited the hospitals. And when I went to the ICU, I realized, you know what? I don't have the strong heart for it, because I almost cried. So I can't be a doctor if I'm going to cry when I see people in pain. So then from there, I was a little bit lost. I won't lie to you. I was a bit undecided because I'd always thought I was going to do medicine. So fortunately, the school that I went to, there was a career guidance office that was tailored towards leaving high scholars. So I didn't actually think I would go to them, but then I realized that I had no plan for what I was going to do for my university. So then we sat down and we said, okay, if you can't do medicine, what else can you do? So at the core of it, I realized that what I actually like is helping people. So if I can do anything to solve problems and help people, then that would be great. I hadn't thought about engineering of any kind. I just always said, I'm going to be a doctor. So that was the first breakthrough that happened. I was still, I think that was my last year of high school. But then now we needed to narrow it down. Okay, engineering, what type? So because the conventional ones are, your mechanical, your electrical. Yeah. I actually hadn't heard about civil, actually. I hadn't heard about civil until I went to the career guidance. I was like, oh, okay, there's civil, etc. So we then sat down and said, okay, my strengths actually lie back then and still now, I think, maths and chemistry. Physics wasn't really my strong suit, and neither was actually bio, which is interesting since I'm now in a biotech space. But so then we focused on maths and chemistry. Like, okay, let's see what we can find. And so that's when I first found out about chemical engineering. And until I started my first year, I thought chemical engineering was chemistry, which is it's the worst misconception to have about chemical engineers, because we're not all about chemistry. Yes, chemistry does play a impact, like play a factor, sorry, but we're not just chemists. So it was then when we discovered what chemical engineering is and where it can be applied. So basically what a chemical engineer does is that we design, develop processes that that take a raw material. As long as you have a raw material that you need to process until you get to your final product, you'll always have a chemical engineer there. So as long as it's maybe something from A to B to C all the way up to Z, as long as it's a process, then you'll find a chemical engineer. So the best way to think of us is process engineers as opposed to just chemical engineers. So with that in mind, we then realized that there actually are a lot of fields that we can go into. I'm not going to go into it yet. I'm still talking about my background. But then I realized that having chemical engineering as a degree wouldn't be like limiting me to just being in one field. There are actually so many areas where we can fit in as chemical engineers, but we'll talk about that later. So chemical engineering was one of my options. The other one was biomedical engineering, because I still wanted to be in that kind of field, but then unfortunately I wasn't accepted into it.
Which field?
So because I wasn't keen to stay in Zim. I wanted to leave. I don't think chemical engineering was at the university that I wanted back home. So then I opted to come to South Africa. It wasn't too far from home. So yes. So when I got into another Civ Eng was also my other option, because it's not too much physics. Physics is there, but it's not too much. Am I lying? Okay. I want to lie.
Not much. Unless you're doing something like hydraulics. I think if you're doing like hydraulics, water engineering that you get, I think I remember fluid mechanics, and that's the unit from campus, of course, is the thing that was closest to physics. But I think it's not really that much. Yeah.
It's not really that much.
That's a very
that was background. My other option. I was like, okay.
Yeah. Now you've talked about where this began and the career coaching and everything. How was your undergraduate studies? How did that go?
Okay, so initially I remember my first year was very challenging. Because first of all, being away from home, that was my first time being away from home, and then realizing how much maths is involved. Is what we actually do is we design equipment. We're part of the designing team, because obviously you have your mechanical engineers and your electrical engineers, making sure that the equipment that is, say for example, we want to produce B for A. So what we do is we look at, okay, what are the chemical properties of A? How does it behave as a fluid? If it's a liquid, if it's a solid, if it's a gas, how does it behave? And how is that going to influence the reactor, so the piece of the equipment that you're going to use to put A into, such that you can then create B? So all of that uses a lot of mathematical models, a lot of computational tools, where you need to understand that, okay, because A is like this, if it's a liquid, it has to do this. So my instrument, my reactor, needs to be able to, if there's any heat that's produced or released, your reactor needs to be able to withstand all of that. So that's just a little snippet of how we come into processes in general, because you'll find that we're actually useful in different areas, different fields. So that was a surprise to me.
You didn't expect a lot of mathematics?
I did not expect that.
What did you expect? Chemistry?
I didn't. I honestly, I did. I thought that surely there's a little bit more chemistry. No. So chemistry was only compulsory in first year. That was the only time we did chemistry as a compulsory elective. And then maths was compulsory all the way. But another thing that I was surprised was all the teamwork. So basically, at every single semester, you're grouped with 3 or 4 different individuals. And after every 3 weeks, so how it's structured at UCT is that 3 weeks you have a module where they're teaching you maybe, let's say, reactions, chemical reactions. And then in the 4th week, you have a project that's centered around chemical reactions. So what they do in that project week is that you're grouped with 4 people, not your friends, it's it's randomized, and you have to work together.
Project?
Sorry?
What kind of project are you doing?
So it would be either designing a piece of equipment that's in the process overall. So for example, say you're trying to make coffee. You have the initial stages where you have the plant, and then you have to grind it and mill it, and then you have to ABCD all the way up to. So at that initial stage, okay, I have to design the grinder to make sure that it actually works to efficiently as well, like motor power and all of that. You need to do that. So in doing that, go ahead.
Could I just cut in? So you're designing like you're saying, like you guys, you're designing an equipment. Somebody does themselves an equipment in chemical engineering. Where do they meet?
Where would we need equipment? Okay, so
in chemical engineering.
Yeah. So let's say okay, let me talk about chemical reactions. So let's say you've had your reaction, you've had A turn into B, but then the B that's been produced, now it's at such a high temperature. Now you need to cool it down to a certain, maybe you need to cool it down to room temperature, because at high temperatures, maybe you might experience, maybe the chemical compound may be either harmful or it may be volatile such that it releases fumes. So you need to, as a chemical engineer, you need to design a heat exchanger. So a heat exchanger basically makes sure that a fluid is at the right temperature that it's supposed to. If it's too hot, it cools it down. And if it's too cold, then it heats it up. So let's say in the
heat exchanger, is it an equipment or is it like it's an equipment? So then that would be like mechanical engineering, or wouldn't it be?
So we work with our mechanical engineers. So what we need to do is to ensure that the material that's used to build this equipment is strong enough or is the right grade. If it's stainless steel, it has to be the right grade. If it's thickness, it has to be the right thickness. If it's corrosion resistant, it has to be corrosion resistant. So that's what we look into. And then we give those kind of specs to the mechanical engineers to obviously then build it. And then the electrical engineers then have to wire it and all of that. But then we just need to make sure how we come in is to make sure that it's not going to blow up. Like you start your reaction or you start whatever process, and then all of a sudden nothing happens, or it explodes, or it, so we make sure that it's efficient and that it's safe. Hand in hand with mechanical engineers.
Thank you so much, Rufaro, for that. I think when we start talking about the career paths and where we are working, I think we're going to get the picture more clearly. But then also when you're talking about that, I thought we could add something on how, where else, because you talked of you guys are working with the mechanical engineers. So maybe later when you're talking about that, you could tell us maybe if you work with other engineers, if you work with civil engineers, if you work with electrical engineers, and what it is that you guys do with the engineers. So we can look at that later. Please tell us something about the MSc you just completed and how that was.
Okay, that's fine. I can answer it together because I'm working as a research assistant actually at the Center for Bioprocess Engineering. So that's a research group that's within UCT. So what I did for my MSc was how good is your science? If I say enzymes, do you know what enzymes are?
Yeah, I remember from chemistry.
Okay, perfect. Okay,
From
perfect. So
biology. From biology.
Yes, nice. So
Mm-hmm.
basically, what I did with my MSc, we there in the past 30 or 40 years, there's been this specific enzyme that was isolated from a mushroom. So what that enzyme
Mm-hmm.
does is it produces how deep can I go? So basically, it would. Hey, I'm trying to make it. How good is your chemistry? If I say
I'm
oxidation,
already intrigued. I'm already intrigued because you're telling us an enzyme from a mushroom.
yes, an enzyme from a mushroom, yeah, literally. So what they did, they
Okay.
isolated it and realized that it has certain properties um, that make it very useful when it comes to trying to turn something that's basically non-reactive into a valuable product. So if I say something like alkane, alkane, do you remember alkanes? Okay.
Nah.
Styrene. If I say styrene, styrene is like a
Oh my
chemical.
lord. That's chemistry. This is
Okay.
so deep.
How do I describe?
You're taking
It's
me
a
way
certain
back
chemical.
to high school.
Okay, sorry. I'm realizing. Okay, let me come back. Let me come back. So basically, if we have a chemical, a naturally
Yeah.
occurring chemical, that is definitely like it's difficult for it to react under normal circumstances. It just doesn't react. But then the thing is, you can get valuable products from it if maybe, say, you add an oxygen to it, or you add a nitrogen to it, or you add something to. So by itself, it's very useless. But then through a
Mm-hmm.
reaction, it can become something that's
Mm-hmm.
useful, right? Valuable. So
Mm-hmm.
conventional methods, conventionally, you'd need to use catalysts. So a catalyst is something that speeds up the rate of a reaction. All right.
All right.
Okay. Yeah.
I to
So
get it.
conventionally, okay. So traditionally, what would happen is, say you want to make an alcohol from something that's it doesn't react. So what would usually
Yeah.
be done, they would use metal type of catalysts. So that means extracting metals from the ground and then creating a catalyst such that you can get your valuable product. Because remember, catalyst speeds up a reaction. So what this enzyme
Yeah.
does is that it does the same thing, but it does it at lower
Mm-hmm.
temperatures. So if you were to take your
Okay.
metal catalyst, you'd need like temperatures of about 100 to 200 degrees Celsius. But then what this enzyme
Okay.
does is it makes that product, but at literally room temperature. So you can
Oh my
still
god,
get
that's
your,
fascinating.
yeah, but
That's amazing. And
like,
but
yeah, the problem,
you're saying
the
mhm.
main problem with using this enzyme is that after a certain time, it dies.
Okay. How long?
So it just, at some point, the chemicals become too strong for it because remember, a mushroom will be just chilling in the forest and it's just doing its job. It's in nature. It's in
Uh-huh.
its natural environment. But if we now take that
Okay.
enzyme out of the mushroom and we now put it into a more chemical environment, it becomes a little bit uncomfortable. So it will be able
All
to
right.
perform the reaction, but at a
Okay.
slower rate, and at some point it dies.
Oh,
So
uh-huh.
my thesis was seeing what conditions were optimal for me to get a high product, a high conversion.
Yeah.
So that means I needed to change the chemical environment that I was adding the enzyme into it and tracking the life of the enzyme or the activity of the life to see, okay, at
Yeah.
what point does it die? And what's the environment looking like at that point? So I would change various things like the temperature, like the pH or water or so, and in doing so tracking the life of the enzyme as well as how much product it made. And then I needed to apply a computational model to it to see, to sort of have an understanding of the kinetics, or basically the lifetime of the enzyme. So that was basically my entire thesis. And
Okay.
I did that at a very small scale. And then the hopes were to be able to do it, obviously, at larger scale so that it can become a viable process, obviously, because you don't want to do this and then, yeah. So basically it was like a proof of concept type of project to see, okay, at this small scale, like I think it was 20 milliliters that I worked with, how viable is this process with this enzyme? Yeah.
Okay.
Yeah.
So how many mushrooms did you need?
So fortunately, there is a company. No, actually, it's a university. University of Free State, which is in South Africa. They already do the entire extraction. So what I just needed to get from them was a little bottle that they'd already extracted, purified, and packaged.
Okay.
So they'd already done the first part of it. Yeah.
Okay.
Yeah.
I thought you were going to look for mushrooms. I literally thought you were going to look for mushrooms in the field.
That would have been exciting. I would have liked doing that.
Yeah.
Yeah. But yeah.
That's
and then
currently, that's really
sorry.
I was saying that's quite an interesting project. And I know I have very little information of what chemical engineering is, and now you're teaching us. But then I find that project really interesting, that you're using mushroom as a metal catalyst. I find it really interesting. And I was wondering, did you find out how long it lasts, the lifetime, and if this is something, if it's scaled, because you're saying that you'd like to see it being scaled. If that happens, then how would it help in the chemical engineering field?
Sure. Okay. So I don't know if you remember my post where I said sometimes research works, sometimes it doesn't work. So
Exactly.
So it worked up until the longest that I could keep it alive was about 16 to 24 hours. And then at that point, it just died. So what now needs to be done? So instead of scaling it up, because obviously you don't want to scale up something that dies, that's not viable. So now what needs to happen is it's a technique called protein engineering. So basically what they want to do is to maybe change the genetic makeup of the enzyme such that it can last longer, which is a whole other research project on the side that needs microbiologists. So as you can see, with my project, like in the research group that I'm in, we are chemical engineers, we are microbiologists, we are biotech specialists, we are chemists, analytical chemists. So right now, the research group that I'm in, it's so diverse and multidisciplinary, and in the sense that, yes, I'm a chemical engineer, but some of the things that I'm doing lean more to microbiology or lean more to chemistry. So, but I still fit in. So that just shows that, with chemical engineering, there's a lot that you can do. So right now, actually towards the end of the year, I'm still waiting for a new project, but towards the end of the year, the project that I worked on, so I'm more into the biotech space. So some of the collaborations that our research group works with involve pharmaceutical companies. So the company that I was doing research for, it's called Afrigen. So basically they work with vaccines. So obviously after COVID and all of that, there was a big rush, as in so many more African countries were now trying to produce the vaccine by themselves, because otherwise before then, vaccines. So what I needed to do in that sense, I didn't work exactly as a process engineer, like in the lab, but I worked more as a consultant. So being a chemical engineer, you get equipped with so many different skills that it also involves data analysis skills. And even with the projects that we would do in undergrad, instead of, and we didn't just design equipment, we would also cost them. We'd also see what would be the environmental impacts of that whole process. So we'd look at everything in a holistic view.
Okay.
So with that, and also because it's projects, so there are also project management skills that you get from doing that for 4 years, as well as presenting. So you present your findings as well every single year, twice a year at least. There's a presentation where you have to present, and it needs to make sense as well. So with those skills, there was a project that we worked with this company that's called Afrigen. So basically, they were comparing two processes that they had developed, that were developed actually like globally, to see which one was more economically viable than the other. And so what they wanted to know is if they could change a certain condition or change a certain equipment. So instead of using stainless steel reactors, they wanted to use a different type of material. And so what I needed to do was to see whether that would be viable, how much it would cost, and the implications of making that change, and whether it's feasible. So I didn't necessarily, I wasn't in the field, but what I needed to do was there's this, so we also do computational skills are also involved here. So there's this modeling software.
Rufaro, by the way, I have to say you are literally answering the questions I had in mind. And thank you so much, because now I'm starting to see how the engineering part is coming out, because now you're talking about cost-benefit analysis, the data analytics and softwares and things like that. And you're starting to bring out now the picture of the engineering part of it. And when you're talking about the vaccines, I thought to myself, you wanted to become a doctor, and that's just like medicine. Literally. You're doing it. You were a doctor and an engineer. It happened. Yeah. Right?
Oh wow. I hadn't thought of that. Oh my god.
That's what I thought. And I'm just saying to myself, like, all this time you've been sounding like a doctor.
Oh my god.
So it's like you achieved one of your dreams. Right.
That's so amazing. I hadn't made that link yet. Wow. Thank you for sharing that with me. Thank you. Wow.
I just thought of that.
No, thank you. You're welcome.
You're welcome. So please finish your thoughts.
Yes, thank you. So initially what I needed to actually do was to develop the entire flow sheet. So starting from scratch, from raw material up until final vaccine product. And then in that, should I show you this? Okay, no, it's IP protected. Sorry, I was going to share my screen and show you what the process flow sheet looks like.
You can. Is it?
I can.
I think you can present. Yeah.
Okay.
Let's finish your thoughts.
Oh, okay. But yes, basically, I needed to develop the entire flow sheet from scratch. And then from there is where I needed to work out what the costs were for each individual equipment, as well as the raw materials that were needed. So it was quite challenging, because also I needed to present that information back to the African representatives, as well as compiling a report that explains everything that I did, my research findings and conclusions and all of that. So it was very interesting. And I think I've been in the research space for a couple of years now, and it's made me want to sort of not stay, but I really do enjoy research. So applying scientific theories or concepts and actually using it to solve problems or real application of it. So I've been enjoying it, and I'm hoping to stay in that field, as well as like in the pharmaceutical space. Yeah.
Mm-hmm.
So essentially,
Mm-hmm.
every step of
Mm-hmm.
the way, all those little equipment pieces, we would have designed them. Everything from the mixers to we would have designed them, but not obviously by ourselves. We also need your mechanical, your electrical. So I'm always going to say this because I don't want to seem like, oh, we know everything. No, chemical engineers do not know everything. We don't. We work together. That's a very important thing
Exactly.
that I learned throughout my chemical engineering journey is that
Yeah.
we work together. We need to come together to solve solutions, to solve problems.
Mm-hmm.